Hi students, this is Mr. Bob, and this is part 2 of topic 3.1, heat, temperature, internal energy, and specific heat. And again, just a quick reminder, before watching this video, you should have completed your first pass of the focused note taking on sections 14.1 to 14.5 in Gene Coley. Have those notes in front of you, have a colored pencil or highlighter ready, and then also you should have watched part 1 of this video, which is or part 1 of this topic, which is a previous video. And just a quick reminder, recommendations while doing this video, while taking notes while watching this video: avoid mindlessly copying, and please actively listen and selectively write down the things or make them stand out in a different color, things that you see me emphasize or seem key to you. Just think of this as kind of like you're filling in the blanks, so to speak, of maybe some of the things that the book didn't cover as well or didn't emphasize as much as I'm covering here. And for the sample problems, although there aren't any in this video, make your brain think about it, how you would solve it, work it as far as you can yourself. Then always stop the video as you need to, or play it at 1.5 times speed if you can keep up with the conversation, if you need more clarification. And if you're still confused, you should be basically marking that section of your notes, that point in your notes, to kind of bring up to a classmate or to me. Okay, again, the essential question is, how can we apply the concepts of heat, internal energy, and the law of conservation of energy to analyze calorimetry problems? So here we go. What we're going to do here is, I'm going to put this down here. Where am I going to put this? That's it. Let's suppose we have a thermometer and it's frozen in ice, okay? And the ice is cooled to a temperature of -20, okay? And then we slowly add heat to that block of ice. And then we plot on the bottom there. You can see we're plotting temperature versus heat added. So let's see what happens here. Notice, as time goes on, the temperature of the block of ice is going to rise. It's going to rise from that -20 degrees Celsius, and it's going to reach somewhere around 0 degrees Celsius. And then interestingly, it's not going to continue to rise. Like, it's going to be a period of time where the fire's still going, but the temperature staying stable or staying the same, as you can see there by that dotted line. And then at some point, it'll then keep going upwards afterwards. And at that point, what we've done is we've reached the melting point and we've transitioned through the melting point, and what we have is water. No longer have ice, we have what we call water. Okay? And then we get to 100 degrees Celsius, a similar thing happens as previously happened at 0 degrees Celsius. We'll keep adding energy to the system, and yet the temperature won't change for a while. It'll stay at that 100 degrees Celsius plateau. Eventually, with enough energy added, you've reached the boiling point, and eventually with enough energy added, the temperature will begin to rise again. And at that point, what you have is you have steam. And in fact, if the temperature gets above 100 degrees Celsius, we have what we call superheated steam. If we were looking at the special words we use to mark these transition points, melting point, boiling point is kind of like on the way up when the temperature is rising. On the way back down, you would call it a condensation point if a gas is turning into a liquid. And you would call it a freezing point if you see a liquid turning into a solid. But let's take a look under the hood, so to speak, and get a sense for what's going on in terms of the internal energy of the water, or the H2O. Okay? And remember, internal energy from the last video is made up of two components. It's made up of the kinetic energy and the potential energy. And notice the kinetic energy in green here, on the diagram there, on the phase change diagram, or the temperature versus heat added diagram, you can see in green, those sections in green are the ones where clearly the kinetic energy, internal kinetic energy of the H2O molecules is increasing. Okay, and we know that because we know kinetic energy, a measure of kinetic energy, of the average kinetic energy, is the temperature. So when the temperature goes up, we know the average kinetic energy of the molecules is going up. What's happening in those other parts, those flat parts? No temperature change. Well, remember, the other part of internal energy of a system is potential energy. So in that case, what we have going on is the potential energy of the molecules in the system is increasing. And that tells you that basically that's the type of energy that's receiving all of the energy input from the heat that's being transferred to it. So in other words, to kind of sum it up, what happens during the phase changes? The thermometer only measures internal kinetic energy. Since the temperature isn't changing during that phase change, we know the kinetic energy must not be changing. So the heat, it gets stored only as potential energy during the phase change. In terms of molecular behavior, you can almost think of it this way, and we'll use this analogy a couple times during this year. You can think of a molecule as kind of being in a well of sorts. And when we get into the phase change, that molecule is receiving energy still, but the energy it's receiving is only just allowing it to rise up a little bit in the well. And it's only until it reaches the very top of that well that it's able to kind of break loose of the bonds, the intermolecular bonds, that is keeping it kind of close by the other molecule that's close to it. And so you have to basically put enough energy into the molecules to allow them to break those intermolecular bonds, and that allows them to transition from either solid to liquid or liquid to gas. Okay, let's talk about this concept called specific latent heat. The word latent means hidden. And so the reason the term is used is because when we get into phase changes, you cannot tell from temperature that heat is being lost or gained by a substance because, remember, the temperature is constant. It's the latent heat that is responsible for the phase changes. And I guess latent is not a different type of heat energy. It's just, we're just saying that the energy input during those transition periods is hidden from us in the sense that temperature isn't changing. And that's why we call it latent. There's a formula, and just like we had a formula to figure out or to equate the heat input with the temperature change and the mass of an object, similarly, there's an equation to do that for these transition periods, these phase changes. It's called the specific latent heat formula. And you can see here it says Q equals M times capital L. Capital L, I want you to think of as the analogy to lowercase c, the specific heat capacity. And this specific latent heat basically is a measure of how hard or easy it is to change the phase of a certain substance. If you have a large L, that means a substance requires a lot of energy to change the phase. If you have a small L, that means a substance can easily change phase with little energy. Okay. Notice there's no temperature change in this formula, and that makes sense because there is no temperature change during the phase changes. Okay, so the units for L, again, if we do this like we did, let's go back for a second. L equals Q over M, which equals joules over kilogram, right? So joules per kilogram, those are the units. Okay, now like we did with specific heat capacity, I just want to show you a few substances. There are two phase changes, remember, the solid-liquid phase change, and there's also the liquid-gas. And so with those two plateaus, there's two different latent heats. One is called the latent heat of fusion. That would be the one that mediates between solid and liquid forms. And the other one is latent heat of vaporization, which is the transition from liquid to gas or vice versa. Let's take a look at these values here for four substances: water, mercury, oxygen, and gold. Again, if you take a moment to kind of make some observations, again, it's interesting that the metals, like mercury is a metal, the metals tend to have smaller latent heat of fusions and also smaller latent heat of vaporizations. Although gold is pretty tough. You can see gold kind of is an exception there. But again, the important thing that I want to make sure you realize is that water is by far the most demanding. The latent heat of fusion and the latent heat of vaporization of water is just tremendous. In fact, the latent heat of vaporization, this number here, look at this. This is like 10 times more than mercury or oxygen. So it takes 10 times more energy to take a certain mass of water and change it from water to gas as compared to mercury or oxygen. And you kind of have an intuitive sense of that, right? Because when you boil pasta, for example, man, I don't know about you, but for me, it takes a heck of a long time for that water seems to be really hot, but it takes a heck of a long time for you to actually start seeing significant bubbles. And that's why it just takes a lot of energy. All right. Just a few more notes. Why is there no temperature symbol in the latent heat formula? Because remember, there's no temperature change during a phase change. Therefore, there's no delta T in our formula. And this is also why the units for L are joules per kilogram, or in the IB limbo, joules kilogram to the -1. And then a tip here for when to use what formula, okay? When you look at these calorimetry problems, if you're looking at figuring out something related to a phase change, you're going to use Q equals M times capital L. Heat energy equals mass times the latent heat of a specific latent heat, because the delta T is 0, okay? If you see a temperature change or you're going through a process where there is a temperature change, you're going to have to use Q equals MC delta T. Okay. A few more important concepts and then we'll be done with this video. One is thermal equilibrium. Thermal equilibrium is this fancy word that just basically means it's a condition where two substances will no longer transfer energy, heat energy between them. And when will that happen? That'll happen when the two substances reach the same temperature, right? Because we know heat energy goes from a hot substance, meaning higher temperature substance, to a colder substance, lower temperature substance. So once they reach the same temperature, they are said to be in thermal equilibrium, and there will be no energy transfer between them. Final vital concept is this one. In a closed system, and also we think about it as an isolated system, the total heat transferred in or out of that system must equal zero. And this is going to be very important in problems you're going to look at. And so we can express this several ways. One, we can think of it as the heat lost equals the heat gained. We can also think of it as the energy out of one part of a system has to equal the energy into another part of the system. Or we could look at it from a mathematical perspective, a little more mathy. The sum of heat transfers has to equal zero. And if you think about it, this is just another way of expressing that law of conservation of energy that we've already studied, right? You can't have more heat being received by one part of a system if it's not being given up by another part of the system, right? You somehow have created or destroyed energy otherwise. This concept is absolutely key to solving the calorimetry problems that make up a large portion of this unit. So just keep that in mind. So again, just to emphasize the end of this video with the essential question, the important thing here is that you have the foundation of understanding what heat, internal energy, and the law of conservation of energy and how it applies with thermal equilibrium, with the idea of an isolated system, because from here on forward, you're going to use this knowledge to sort of analyze calorimetry problems and also to help you with the lab that you're going to do with your group. All right, thanks for everyone.